All right, hello y'all. Today we're doing drill 6. Let's just get into it. Aspirin, one of the most widely used drugs in the world, can be prepared according to the equation given below. Something to quickly notice is that if you count it all up, this is already balanced. That's perfect for us because we'll be doing stoichiometry. Balanced. A student reacted some salicylic acid with excess ethanoic anhydride. Impure solid aspirin was obtained by filtering the reaction mixture. Pure aspirin was obtained by recrystallization. Table 9 shows the data recorded by the student. Uh, I determine the amount in mole of salicylic acid used. Well, for this one, we're just converting our mass used in grams, 3.15, into moles. So what we need is the molar mass of salicylic acid, which if we go ahead and take this formula right here, we see that we have 7 carbon masses, we have 6 hydrogen masses, and we have 3 oxygen masses. So all in all, we're going to have a mass of 138.13 grams per mole. So we can take 3.15 grams, do 1 mole on top, and divide by 138.13, and we will get an answer of 0.0228 moles of salicylic acid. All right, moving on to number 2. Number 2 says calculate the theoretical yield in grams of aspirin. So what we have to do is take our moles of salicylic acid, 0.0228 mole of salicylic acid. I'm just going to say SA because I don't want to write it out. And we're going to go ahead and convert that. Now we know it's a 1-to-1 ratio because we looked at the balance equation already. So it's 1 mole SA to 1 mole, I'm going to say AS for aspirin, even though I know that that's arsenic, but I don't feel like writing out aspirin. So then 1 mole of aspirin. And again, we have to do the conversion. If we take this and we measure it out, we see that we have 9 carbon masses plus 8 hydrogen masses plus 4 oxygen masses, which is going to give us a grand total mass of 180.17 grams. So we'll do 180.17 grams aspirin. Mole of aspirin, mole of aspirin, mole of salicylic, mole of salicylic. And we get an answer of 4.11 grams of aspirin. You'll notice that's actually way less than the amount of aspirin they obtained. That's okay, we'll address that in number 3. Determine the percent yield. So that is our actual yield, 2.50, divided by our theoretical yield, 4.11, times 100, so we get a nice percent, and we'll get 60.9% yield. All right. Now, number 4, state the number of significant figures associated with the mass of pure aspirin obtained. That's the first part, 2.50. That is 1, 2, 3 sig figs. This 0 is significant because even though it is trailing, there is a decimal. So we have 3 significant figures. And then calculate the percent uncertainty associated with mass. They said that it is 0.02 grams plus or minus. That means that we could be off by a total of 0.04. That accounts for 2 above and 2 below. 2 meaning 0.02. So we will take 0.04 grams and divide it by our mass, 2.50. And again, we're going to multiply by 100 because this is a percentage, and we will get a percent of 1.6%. So 3 sig figs and 1.6% are our answers. All right. Lastly, V5. Another student repeated the experiment and obtained experimental yield of 150%, way over. The teacher checked the calculations and found no errors. Comment on the result. So we know that the math is correct, which means that they maybe had 2 much product. 150% means they probably had somewhere around 6 grams, 6.22 to be exact. But they had too much product. So we have to figure out why they might have too much product. Well, the first thing they say is that they get impure aspirin in this experiment, and then they filter, or they get impure aspirin by filtering, and then they recrystallize. So we would likely say that we likely have an impure result. This isn't pure aspirin. We've got some excess stuff. Furthermore, this was gone by recrystallization. Recrystallization. It may still be wet. It may still have solvent and not fully dry. There's a bunch of different answers. Both of these would attribute to more mass. Attribute to more mass. All right, I hope that helps, and good luck.